Look up. Not the way you usually look up, quickly between tasks, between thoughts. Look up the way our ancestors did, the way they had no choice but to do, on cold, open ground, with nothing between them and the infinite but darkness and wonder. For most of human history, the night sky was the greatest question we had ever been asked. Those lights, those patient, unwavering lights, what were they? Gods? Windows? Fires lit by beings we could not imagine? We built mythologies around them. We named them after heroes and beasts. We charted their movements and called it divine order. And for thousands of years, the question of what was out there, truly out there, went unanswered because we had no way to ask it properly. But here is what every human being who ever lived beneath those stars believed, without exception, without doubt. Our world was the world. The ground beneath our feet was the center of everything. The planets and stars orbited us. The cosmos had been built around this one small blue breathing place. Then, in the 16th century, a Polish astronomer named Nicolaus Copernicus did something quietly radical. He moved us, not physically, but conceptually, cosmically. He placed the sun at the center, and Earth became just one of several worlds circling it. It sounds like a demotion, and in some ways it was, but it was also an invitation, an opening, barely a crack at first, into something so much larger than the story we had been telling ourselves. If Earth circles the sun, what do the other lights circle? If we are a planet, are there other planets? And if there are other planets around other suns, could some of them hold, in some corner, in some form, something like life? This is the question that would take 4 more centuries to even begin answering. The word exoplanet is a simple one. It means literally a planet outside our solar system, a planet orbiting a star that is not our sun. It is a word so ordinary sounding that it almost conceals the enormity of what it describes. Because what we are really talking about is other worlds, other Earths maybe, other skies, other dawns breaking over mountains we have never seen and never will, oceans that have never known a human footprint, atmospheres breathing chemistry we can barely imagine, and perhaps other eyes looking back across the dark, asking the same questions we are. For most of recorded history, exoplanets were theoretical. Philosophers suspected them, scientists hypothesized them, but no one could prove they were real. The problem was simple and devastating. Stars are incomprehensibly bright, and planets are incomprehensibly dim. Looking for a planet next to its star from across interstellar distances is like trying to spot a firefly hovering next to a searchlight from 100 kilometers away. So for centuries, the questions sat there, unanswered, like a locked door in the middle of an open field, until 1992, until 2 astronomers working with a radio telescope in Puerto Rico detected something strange in the timing signals of a pulsar, a dead, spinning star, and realized that the irregularities could only be explained by the gravitational tug of planets orbiting it, right there. The first confirmed exoplanets were found not around a living star, but around a corpse. That is where this story begins. 3 years later, in 1995, astronomers Michel Mayor and Didier Queloz announced the discovery of a planet orbiting a Sun-like star, 51 Pegasi, just 50 light-years away. This planet, later named Dimidium, was unlike anything anyone expected. It was a gas giant, something like Jupiter in mass, but it orbited its star in just 4 days. 4 days! Mercury, the closest planet to our own Sun, takes 88. This world was so close to its star that its surface temperature exceeded 1,000 degrees Celsius. No one had predicted this. The models were wrong. The universe had answered our first real question with something we hadn't even thought to ask. That is the thing about the cosmos. It does not care about our predictions. It simply is, vast, strange, older than any story we have ever told, and full of surprises that our best theories did not account for. But the door was open now. From that first confirmed exoplanet around a Sun-like star, we have gone on to discover, as of this telling, more than 5,000 confirmed worlds. 5,000, with thousands more candidates waiting to be verified. And those numbers represent only the ones we have found so far, in the small swathe of the galaxy we have managed to examine. The true number of planets in the Milky Way alone is estimated to be in the hundreds of billions. More planets than stars, more worlds than we have names for. Let that land for a moment. We are not alone in having a solar system. We are not special in that way. The galaxy is thick with planets. It always was. We just couldn't see them. But seeing them, actually seeing them, turns out to be only the beginning of the story. The deeper question, the one that makes scientists lose sleep, the one that has propelled billions of dollars of engineering and decades of human genius, is not merely, are there other planets? It is, are any of them like ours? Are any of them the right temperature for liquid water, the right size to hold an atmosphere, the right chemistry to allow the long, patient chain of reactions that on this planet eventually looked up at the stars and asked these very questions? We are right now at the edge of being able to answer that. We are not there yet, but we are close enough to feel the ground beneath us trembling with possibility. This documentary is about that edge. It is about what we know, what we think we know, what we suspect, and what we cannot yet even guess. It is about the science and the philosophy of standing on one small world and trying to understand all the others. It is about the loneliness of the sky and the slowly growing suspicion that we might not be as alone in it as we once feared. Stay with us. The story is just beginning.
Imagine you are standing in a completely dark room, and somewhere in that room, a candle is burning. You cannot look at the candle directly. It is too bright. It would blind you. But you want to know if there is a moth circling it. A small, quiet moth, making tiny, almost imperceptible adjustments to the candle's flame. This is, roughly, the problem of finding exoplanets. Stars are not just bright. They are nuclear furnaces of inconceivable energy, radiating light across years, decades, centuries of empty space. A planet beside a star produces, on average, about 1/1,000,000th of the light its star does. sometimes less. In the earliest days of the search, detecting such a faint signal next to such an overwhelming source seemed almost impossible.
And yet, we found a way. Actually, we found several. The first, and the one that has proven most productive, is called the transit method. It works like this. When a planet passes in front of its star, from our perspective here on Earth, it blocks a tiny fraction of the star's light. We cannot see the planet, but we can measure the star's brightness very precisely. And when the brightness dips ever so slightly in a regular, repeating pattern, that dip is the shadow of a world. Think of it. We are discovering entire planets by watching for a shadow. A dimming of a distant light lasting a few hours, repeating every few days or years, depending on the orbital period. The planet itself remains invisible to us. We infer its existence from its effect on the light it passes through. This method was the engine of NASA's Kepler Space Telescope, launched in 2009. Kepler stared at a single patch of the sky, about 1/400th of the total sky, and watched over 150,000 stars simultaneously for 4 years. It was watching for shadows, patient, precise, relentless. In that one patch of sky, Kepler found thousands of planets. Thousands! In one tiny sample of the galaxy. It was, in scientific terms, a data revolution. In human terms, it was the moment we realized, truly, viscerally, with numbers to support it, that planets are everywhere. But the transit method only works for planets whose orbital planes happen to align with our line of sight. If a planet orbits its star at the wrong angle relative to Earth, it never passes in front of that star from our perspective, and we miss it entirely. This means that everything we have found using this method is a biased sample. The real population of planets is almost certainly even richer than what we have detected. The second major detection method is called radial velocity, and it works on an even more elegant principle. Here is the thing most people do not realize. A star does not just sit there while its planets orbit it. The planets tug on the star gravitationally. They pull it subtly, barely, in the direction of their orbit. So as a planet circles its star, the star wobbles, a tiny rhythmic wobble, too small to see as movement across the sky, but detectable as a Doppler shift in the star's light. Doppler shift. You know this from everyday life. The way the pitch of a siren changes as an ambulance races toward you and then away. When the star moves toward us, its light shifts slightly bluer. When it moves away, slightly redder. By measuring this shift, by essentially listening to the star's light change pitch, we can detect the gravitational pull of an unseen planet. Michael Mayer and Didier Queloz used this method to find 51 Pegasi planet.
in 1995. It is a technique that requires exquisitely precise instruments. We are talking about detecting shifts of a few meters per second in the motion of a star light years away. But it works. And it tells us something the transit method alone cannot: the mass of the planet.
Then there is direct imaging, the most intuitive method and the hardest. Actually taking a photograph of the planet itself, blocking the star's light with a device called a coronagraph, and looking into the surrounding darkness for the faint reflected glow of a world. We have managed this for a handful of planets, large, young, hot ones that glow with their own residual heat and orbit far from their stars. But for small, Earth-sized worlds close to their stars, direct imaging is still beyond our current technology.
For now. There is also gravitational microlensing, a technique that uses the way massive objects bend light, predicted by Einstein's general relativity. When a star passes in front of a more distant star from our perspective, its gravity acts like a lens, magnifying the background star's light. If the passing star has a planet, that planet adds its own tiny gravitational signature to the lensing event. We have found planets this way, including some that appear to have no host star at all, drifting free through interstellar space, unbound, orphaned by some ancient gravitational interaction.
There are rogue planets, worlds with no sun, just darkness in every direction, forever. Consider that for a moment. Consider what it means for there to be worlds with no light, cold and silent and enormous, tumbling through the space between stars for billions of years, with nothing above their surfaces but the faint, equal glow of the entire Milky Way spread across the sky. No sunrise, no seasons, no day. We have barely begun to understand what is out there. Each method of detection reveals not just the existence of a planet, but something of its character. The transit method gives us orbital period and planetary radius. Radial velocity gives us mass. Together, they give us density. And from density, we can begin to infer composition. Is this a rocky world? A water world? A gas giant? Does it have a thick atmosphere? Could it hold liquid on its surface? And then there is spectroscopy. When a planet transits its star, some of the starlight filters through the planet's atmosphere, if it has one. Different molecules absorb different wavelengths of light. So, by analyzing the spectrum of light during a transit versus outside of one, we can detect the chemical fingerprints of whatever is in that atmosphere. We can detect water vapor, carbon dioxide, methane, oxygen from light years away. This is the technique that will, in the years and decades to come, tell us whether any of these distant atmospheres carry the signatures of life. We are not doing this blindly. We are not guessing. We are reading the light,
The same light that has traveled years across space, that has passed through clouds of alien chemistry, that has been subtly, indelibly marked by whatever it moved through, and learning to decode what those marks mean.
It is perhaps the most profound act of reading in all of human history. The universe is writing. We are learning to read. But here is what we must sit with as we continue. Everything we know about exoplanets, we know indirectly. We have not touched them. We have not seen them up close. We infer them from wobbles and shadows and spectral lines. They are, in a very real sense, ghosts, known by their effects, never by direct encounter.
And yet, what we have inferred from those ghosts, from those shadows and whispers and shifts of light, has already shattered everything we thought we knew about how planets form and where life might exist. The ghosts have been speaking, and what they are saying is extraordinary.
If you had asked an astronomer in 1990 to describe what other solar systems probably looked like, they would have described something like our own. Rocky planets close to the star, gas giants further out, neat, orderly, sculpted by the laws of physics we understand. A kind of cosmic common sense. The universe had other ideas. What we have found in the 30 years since the first confirmed exoplanet detections is not a collection of systems that look like ours. It is a zoo. A sprawling, chaotic, breathtaking zoo of worlds that follows its own rules. Rules we are still struggling to understand. Let us walk through it. The first animal you encounter is the hot Jupiter, a gas giant as massive as Jupiter or more, orbiting its star so closely that a year on its surface lasts just a few days. The temperatures on these worlds exceed 1,000 degrees Celsius. Their atmospheres are being slowly stripped away by stellar radiation. Some of them are so tidally locked to their star, one face permanently baked in eternal noon, the other locked in eternal night, that the temperature difference between the two hemispheres drives winds of thousands of kilometers per hour, supersonic winds raging perpetually around a world where one side melts and the other freezes. Hot Jupiters shouldn't exist by our original models. Gas giants were supposed to form far from their stars, where temperatures are low enough for the ices and gas they need to accumulate. So why are they so close? The answer, we now believe, is migration. These giants formed far out, and then, through gravitational interactions with the disk of gas and dust surrounding their young star, or through interactions with other giant planets, they spiraled inward. Over millions of years they moved, and as they moved, they may have disrupted, destroyed, or flung outward any smaller rocky planets that were forming in the inner system. Migration.
The planets themselves move. The architecture of a solar system is not fixed. It is the product of a long, violent, dynamic history. A history of collisions and resonances and gravitational billiards that plays out over hundreds of millions of years.
Our own solar system went through this. There is evidence that Jupiter itself migrated inward early in the solar system's history, then back outward. That migration may be responsible for why Mars is so small, why the asteroid belt exists, and why Earth exists in the form it does. The architecture we live in is not inevitable. It is the result of a specific history. Change any part of that history, and this planet might not be here.
Now, meet the super-Earths. These are, by far, the most common type of planet in the galaxy, and they don't exist in our solar system at all. Super-Earths are worlds larger than Earth, but smaller than Neptune, typically ranging from 1.5 to 4 times Earth's radius. They are so common that their absence from our solar system is starting to look like an anomaly. We appear to live in a relatively unusual place.
What are super-Earths actually like? This is where things get genuinely strange. Depending on their composition, a super-Earth might be a rocky world, like Earth, but with stronger gravity and a thicker crust. A world where plate tectonics may not work the way they do here, where carbon might be locked away underground rather than cycling through the atmosphere, potentially making long-term habitability difficult. Or a water world, entirely covered by ocean, perhaps hundreds of kilometers deep, with no land at all, and a high-pressure form of ice at the bottom of the ocean, rather than a rocky seafloor. What life, if it existed in such an ocean, would have access to? No volcanic vents at the seafloor, no continental shelves? Is an open question. Or a sub-Neptune, a world with a thick, hydrogen-rich atmosphere, something between a rocky planet and a gas giant, possibly with a liquid or slushy interior under enormous pressure. These worlds might be entirely uninhabitable, wrapped in a crushing, opaque blanket of gas. We cannot always tell which type a super-Earth is, just from its radius and mass. The uncertainty is profound. Then there are the mini-Neptunes, smaller versions of our own blue ice giant, with deep gaseous envelopes and no definable surface. And the puffy planets, gas giants with densities lower than cork, their atmospheres so inflated by stellar heating that they would float on water, if you could find enough water. And the ultra-short period planets, rocky worlds that orbit their stars in fewer than 24 hours, scorched to temperatures that make Venus look hospitable. And then there is a class of planet that haunts the imagination in a particular way. Ocean worlds. Not just planets with water,
Planets that may be entirely, globally, permanently ocean. Covered not by a shallow blue film like Earth's, but by oceans hundreds of kilometers deep, pressing down under their own weight into exotic forms of matter. High-pressure ice, despite temperatures above the freezing point, because the pressure is so immense.
We have strong candidates for ocean worlds right here in our solar system. Europa, Ganymede, Enceladus, Titan. Moons of Jupiter and Saturn with subsurface oceans of liquid water, potentially in contact with rocky seafloors, potentially warm enough, potentially chemically rich enough to sustain some form of life.
Imagine those worlds scaled up. Imagine an ocean world the size of a super-Earth. An ocean that has been liquid for 4 billion years. A seafloor dotted with hydrothermal vents, pouring minerals and heat into the water above. Billions of years. Enough time.
Is there something swimming in those depths? We do not know. We cannot know yet. But the question is no longer absurd.
Here is the number that changes everything. Astronomers now estimate that approximately 1 in 5 Sun-like stars has at least one Earth-sized planet in its habitable zone. The range of orbital distances where temperatures might allow liquid water on a planet's surface. 1 in 5. In a galaxy of 200 to 400 billion stars, that translates to tens of billions of potentially habitable worlds in the Milky Way alone. Tens of billions. And the Milky Way is one of perhaps 2 trillion galaxies in the observable universe. The arithmetic is almost too large for the mind to hold. And yet, it is not the size of the number that is most important. It is what the number implies about the nature of life itself. If planets are common, if habitable zones are common, if the chemistry of water and carbon is found throughout the universe, then either life is common, or there is something we do not yet understand about the origin of life that makes it catastrophically rare, despite all these favorable conditions. Both possibilities are extraordinary. Both possibilities demand an answer. There is a question that lives quietly inside all of this science. A question that the charts and data and spectral analyses do not quite reach. If life is possible elsewhere, why haven't we heard from it? This is the Fermi Paradox, named for the physicist Enrico Fermi, who asked it in 1950 with characteristic simplicity. If intelligent life is common in a galaxy this old, where is everybody?
The Milky Way is 13 billion years old. Civilizations, if they arose early enough, would have had billions of years to spread, to colonize other star systems, to fill the galaxy with radio signals, to leave some mark on the cosmos that we could detect. And yet, we see nothing. We hear nothing. The galaxy is silent.
This silence is not neutral. It is one of the most important and unsettling data points in all of science. There are many proposed explanations, and none of them are particularly comforting.
Perhaps intelligent life is simply extraordinarily rare. Not because habitable planets are rare, but because the chain of events required to go from simple chemistry to complex life, to intelligent life, to technological civilization has so many steps, each improbable, that it almost never completes. Perhaps the origin of the eukaryotic cell, the complex nucleus-bearing cell that all animals, plants, and fungi are built from, was such an improbable step that it may have happened only once in the galaxy's history. Here, us.
If this is true, then the universe is full of microbial life, bacteria and archaea, patient and invisible, colonizing every warm, wet rock they can find. But we are alone at the top. Perhaps it is lonely to be complex.
Or perhaps the problem is time. Life on Earth took 4 billion years to produce something capable of radio astronomy. The universe has been making stars for over 13 billion years, but the right kind of stars, stars with enough heavy elements to build rocky planets and complex chemistry, only became common in the last 5 or 6 billion years. We may be among the first technological civilizations. Not the only ones, just the early ones. The galaxy may be waking up around us, slowly, and the signals from others simply haven't reached us yet.
Or perhaps, and this is the most disturbing possibility, civilizations do arise, but they don't last. Perhaps something happens to all of them. Perhaps the same processes that generate technological intelligence also generate the capacity for self-destruction on a civilizational scale. Perhaps every civilization, when it reaches a certain point of power and complexity, faces a reckoning with its environment, with its weapons, with itself, and most do not survive it. This is sometimes called the Great Filter. The idea that some step in the path from simple matter to interstellar civilization is so unlikely or so dangerous that almost no one makes it through. The terrifying question is the Great Filter behind us or ahead of us? If it is behind us, if the improbable step was the origin of complex life, or the development of multicellular organisms, or some other ancient transition, then we are, in a sense, the survivors, the rare ones, the lucky ones. The universe gave us a hard road, and we made it. But if the Great Filter is ahead of us, if technological civilizations, as a general rule, destroy themselves before they become interstellar, then our current trajectory is not just a human problem. It is a universal pattern,
a law written not in physics, but in the nature of intelligence itself. We cannot yet know which of these is true. We may not be able to know for a long time. But the search for exoplanet atmospheres, the search for biosignatures, for the chemical signs of life in distant skies, is quietly also a search for an answer to this question. Because if we find a world with oxygen and methane coexisting in its atmosphere, chemicals that react with each other and must therefore be continuously replenished by some living process, we will know that we are not alone. And if we scan world after world, habitable zone after habitable zone, and find nothing but dead chemistry, that silence will be its own kind of answer. An answer we may not want.
But there is another dimension to this question that goes even deeper. Even if life is common, even if the universe is dense with biology, would any of it be recognizable to us? Life on Earth is built on carbon, water, and a specific set of amino acids. But these are not the only possibilities. Silicon can form long-chain molecules, as carbon does. Liquid ammonia could, in theory, serve as a solvent for chemistry, the way water does for ours. Life at temperatures we would consider lethally cold or lethally hot may use entirely different molecular machinery.
When we search for biosignatures in exoplanet atmospheres, we are searching for the signatures of life as we know it. We may be blind to life as we do not know it. We may pass over evidence of biology without recognizing it because it does not look like us, because it does not speak our chemistry. This is the deepest humility science asks of us. Not just to accept that we might not be alone, but to accept that we might not even know how to recognize what else is there. We evolved to perceive this planet, these chemistries, this form of existence. The universe is under no obligation to match our categories. And yet, we keep looking. We keep building better telescopes, better instruments, better models. Not because we are certain of finding something, but because the alternative, to stop looking, to assume the silence is final, is a kind of closing of the mind that science cannot afford. The question beneath the question is not just, is there life out there? It is, what would it mean for us if there is? What would it mean for our religions, our philosophies, our sense of purpose and uniqueness and value? What would it mean to learn that consciousness, that this experience of being aware, of caring, of suffering, of hoping, has arisen in other forms, in other places, under other suns? Would it diminish us? Would it elevate us? Would it tell us something true about the nature of the universe? That awareness is not an accident, but a tendency? That matter, given enough time and the right conditions, leans toward experience? These are not scientific questions. They are the oldest questions. They are why human beings have always looked up. We are living in a particular moment, a moment so precise in the history of this inquiry that our descendants, whoever and wherever they may be, will mark it with a kind of reverence. We are living in the moment just before we find out. Perhaps not this year,
Perhaps not this decade, but the instruments we are now deploying, the techniques we are refining, the data we are beginning to accumulate, they are capable, in principle, of detecting the atmospheric signatures of a living world. We are building the instruments to answer the question.
The James Webb Space Telescope, launched in December 2021 and positioned at a gravitational balancing point 1.5 million kilometers from Earth, is the most powerful space observatory ever built. Its infrared sensitivity allows it to peer into the atmospheres of transiting exoplanets with a precision we have never before achieved. It has already detected carbon dioxide, sulfur dioxide, water vapor, and other molecules in the atmospheres of worlds dozens of light years away.
It has not yet found life, but it is looking. The targets it studies most closely, most hopefully, are planets in what is called the habitable zone of their stars. That band of orbital distances where temperatures might allow liquid water to exist on a rocky surface. Not too hot, not too cold. The Goldilocks zone, as it is sometimes called.
But the habitable zone is not a guarantee. Mars is in the Sun's habitable zone, and its surface is a frozen, irradiated desert. Venus is almost in it, and its surface would melt lead. Habitability is not just about distance from a star. It involves the planet's mass, its magnetic field, the composition and pressure of its atmosphere, the presence of water in the first place, the activity level of its star, the presence or absence of giant planets in the outer system, acting as gravitational shields against asteroid bombardment. Habitability is an ecosystem of factors, not a single variable. And yet, some worlds seem to thread the needle. TRAPPIST-1 is a red dwarf star, small, dim, and cool, located about 40 light-years from Earth. Orbiting it are 7 known rocky planets, 3 of which lie in the habitable zone. 3 worlds around a single nearby star at distances that could allow liquid water. TRAPPIST-1e, TRAPPIST-1f, TRAPPIST-1g. Names that sound like catalogue numbers and deserve poems.
Red dwarf stars make up about 70% of all stars in the galaxy. They are the most common kind of star there is. And if rocky planets in their habitable zones are common around red dwarfs, then the number of potentially habitable worlds in the Milky Way is even larger than our conservative estimates suggest. But red dwarfs come with complications. They are prone to violent stellar flares, eruptions of radiation that could strip away a planet's atmosphere or sterilize its surface. Planets close enough to a red dwarf to be in its habitable zone are also likely to be tidally locked, one face always toward the star, the other always dark, with dramatic temperature gradients driving powerful atmospheric dynamics.
Could life survive there? Could it adapt to a world of permanent noon on one side and permanent midnight on the other, where the terminator line, that perpetual twilight boundary between day and night, is the most temperate place on the planet? We don't know. And that uncertainty itself is a kind of invitation. One of the most tantalizing recent discoveries is a planet called K2-18b. It is a sub-Neptune world, nearly 9 times Earth's mass, orbiting in the habitable zone of a red dwarf star about 120 light-years away.
James Webb has analyzed its atmosphere, and it has found, alongside water vapor and carbon dioxide, a tentative signal of a molecule called dimethyl sulfide. On Earth, dimethyl sulfide is produced almost exclusively by marine phytoplankton. It is here a biosignature, a product of life.
The signal from K2-18b is tentative. Scientists are careful, appropriately, necessarily careful. It needs to be confirmed. And even if it is confirmed, alternative, non-biological explanations must be ruled out. Science does not announce miracles on the first pass. But the signal is there, and even the possibility, the ghost of a possibility, that we may have detected a molecule of biological origin in the atmosphere of a planet 120 light-years away is the kind of moment that belongs to the history of ideas. We are, right now, in that moment.
The next generation of observatories will go further. The extremely large telescope being built in the Atacama Desert of Chile will have a mirror nearly 40 meters across, large enough to directly image Earth-like planets around nearby stars and analyze their atmospheres in detail. Ground-based and space-based interferometers will eventually allow us to combine the light from multiple telescopes to achieve the resolution of an instrument the size of a continent. We are building eyes big enough to see other Earths. And what will we see?
Perhaps we will see dead worlds, chemically inert, geologically quiet, lifeless. And that will be its own answer, important and sobering. An answer that would suggest life is rarer than we hoped, that the great filter is real, that consciousness is a stranger in the cosmos than we wanted it to be. Or perhaps we will see something alive. Perhaps we will find a world where the spectral fingerprints of oxygen and methane speak of biology, where the seasonal fluctuations in atmospheric chemistry suggest something is growing, blooming, dying, and being reborn, where the faint infrared glow of a planet tells a story of warmth and weather and water, and underneath all of that, something living. We will not be able to see it directly. We will not be able to name it or describe it, or know if it is a microbe or a forest or a mind. We will just know that it is there, that somewhere, around some other sun, something is alive. That moment, if it comes, will be the most important moment in the history of our species. It will not be the end of the search, it will be the true beginning. Because then we will have an answer to the fundamental question of whether we are alone, and all subsequent questions. What is it? How did it arise? Has it ever looked up? Will organize themselves around that answer for as long as our civilization endures. And if we find nothing? If we scan every promising atmosphere and find only chemistry, only silence, only the patient indifference of physics? Even that answer has a beauty to it. Because it would mean that what happened here, on this unremarkable planet, around this ordinary star, in one of hundreds of billions of galaxies, is something almost impossibly rare. It would mean that the fact of your awareness, right now, reading these words and thinking these thoughts, is not just biologically improbable, but cosmically extraordinary. That consciousness may be one of the loneliest and most precious phenomena in the universe.
It would mean that every thought, every love ever felt, every question ever asked beneath a night sky has happened here, and perhaps only here, in the entire known universe. That is not a small thing. That is not a reason for despair. That is the most staggering argument for the value of a single mind that has ever been made. But we are getting ahead of ourselves. The search is still underway. The data is still coming in. The telescopes are still turning. And out there 40 light years away, 120, 1,000, 10,000, other worlds are spinning through their orbits, indifferent to our instruments, indifferent to our questions, carrying whatever they carry. Oceans or deserts, storms or silence, life or the beautiful, careful chemistry that never quite tipped into it. But we are getting ahead of ourselves. The search is still underway. The data is still coming in. The telescopes are still turning. And out there 40 light years away, 120, 1,000, 10,000, other worlds are spinning through their orbits, indifferent to our instruments, indifferent to our questions, carrying whatever they carry. Oceans or deserts, storms or silence, life or the beautiful, careful chemistry that never quite tipped into it. They are there. We know they are there. Hundreds of billions of them, scattered across the dark like embers from a fire too large to comprehend. And we are here, looking. That is the story of where we are, not at the end of the search, not even at the middle, at the very beginning of a conversation with the cosmos that will outlast every civilization that has ever existed on this planet, and perhaps eventually reach across the light years to whatever else is listening. We began with a question: are we alone? We do not yet have the answer, but for the first time in the history of our species, we have the tools to find it. And that possibility, that threshold, that trembling edge between ignorance and revelation is enough to make you look up again. Not the way you usually look up, but the way our ancestors did. With everything. Go outside tonight. Find a patch of sky without clouds. Let your eyes adjust. Give it time the way our ancestors had no choice but to give it time. And then look, not for satellites, not for planets. Look past all of that, into the deep dark between the lights, into the space between the stars where, we now know, other worlds are turning, quietly, patiently, completely unaware of us. We are not the center of anything. We established that long ago. We are one world around one star, in one arm of one galaxy among trillions. The arithmetic of our smallness is almost too clean to bear. And yet, we are the part of the universe that found a way to look back at itself, to ask where it came from, to wonder whether it is alone, to build mirrors large enough to read the chemistry of a world 100 light years away. That is not nothing. That is, as far as we know, everything. The search for other worlds is not really about other worlds. it is about understanding what this one means, and whether meaning consciousness, curiosity, the quiet ache of a question held across centuries is something the universe makes once, or makes wherever it can. We don't know yet, but we are, for the first time in the history of anything, in a position to find out. That is where we are, right here, right now. Look up.